Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.12, 20-year-old commit, crazy optimization, and more coming up. So yes, today we are going to talk about the Linux kernel 6.12. So this release is a crazy one. We have a lot of new things, and it's also supposed to be a long-term support release. So this should be interesting. Now, there is no confirmation for the long-term support part. Sadly, that's something that comes way later. But for now, we can assume that it's going to be this way. Now, 6.12 is the biggest kernel we've had of the year. So we have a bunch of good features. And because Linus left us with the smallest message of the year, we can get right ahead into the features. Let's start by talking about Preempt RT, also called Real-Time Linux, which was added to the kernel after 20 years of work. Now, there was a little celebration with a golden commit. That was cute. But what even does a real-time kernel? What doesn't change? Well, inside of a standard Linux kernel, if you run a command or if you run a script, let's say, it's going to vary in the latency that it takes to finish each action inside of that script. And it may take more or less time from one time to another execution. Now, inside of a real-time kernel, what we should see is that the script should always take the same time to finish, and inside of that script, each command should take the same time each time it is executed. Now, the big reason why this is useful is because in some application, one good example would be controlling a CNC. Well, this is vital because you cannot really just hope for the latency to be the latency that you think of and just go with it, because it would, well, mess your print or mess your cut, or, well, if you're using it in the automotive or aviation industry, well, you would have some big trouble. So in those cases, we need to have predictable, repeatable latencies for each command, and this is what the real-time kernel provides. So it's a big improvement, something that we were waiting for a real long time. Some people, maybe like me, have messed with CNC Linux, which was something back in the day. Anyway, let's stop being a little bit of a boomer here, and let's go to our next big change, which is the extensible scheduling class, also called SCHEDX, which was added to the kernel. Now, what even is SCHEDX? It's for managing kernel scheduling policy via BPF, the Berkeley packet filter. Now, remember, the Berkeley packet filter allows us to have some small programs that we can make and we can implement into the kernel from the user space. So what it allows us in practice is to be able to change a running computer scheduling policy. So you can tell your computer, hey, let's say I'm running a game, I need this special scheduler that optimizes for that game, and I throw it inside of SCHEDX, and now SCHEDX can run that optimized scheduler. And now, let's say I'm doing something else, I'm watching a movie, so now I want my optimized scheduler for that. Well, I'm throwing my code for this new scheduler made for movies, I throw it in SCHEDX, and now it runs. So it's really useful because it allows fast iteration and maximum amount of modification of a scheduler without having to recode a whole new scheduler inside of the kernel. It of course doesn't fix everything, but it makes creating new scheduler for precise application really easier. And while we're talking about easier, let's talk about VFS that makes two big change to the kernel. The first one is the ability to have bigger block size than the system page size inside of a given file system. This is huge because now with those bigger block size, you may be able to take advantage of some optimization of your hardware with a given file system that would allow you to get more performance, faster storage, or even just more optimized storage. Or if you've seen my ext2 video, you know that a file system like ext2 can store more data if it's on a bigger page size. So it is really important that we have this ability, and now it's been implemented, and it's also been implemented inside of XFS. So XFS user can now format their drive with a bigger block size than their page size. And while we're talking about VFS, let's just talk about the fact that they reduced the file structure size, which is really important because each time that we open a file, so let's say that we're reading a document, it's going to create a file structure that will keep that file inside of memory. Now, that file structure has been reduced from 232 bytes of data to 184 bytes of data. The big reason why they managed to reduce it by that much is because they cut down on things that really shouldn't have been there by default in the first place, making most things that were somewhat useful but rarely used as an optional thing that you can add in another way. And our last featured change is PKVM, protected KVM, which we are going to need to a little bit zoom out and try to understand some things about Android. Now, there's always been a little bit of a problem with Android, is that it was really fragmented in terms of the kernel and in terms of hypervisor. Android has always been all over the place. You see, one phone model or one tablet model would have vastly different kernels and vastly different hypervisor, or maybe no hypervisor at all, which would make Google's job of trying to make everything as simple as possible from an application point of view really hard. So there was some initiatives that were made to try to fix that. The first one was GKI, which is generic kernel image, which was there to standardize the kernel that Android should use so that the vendor can take that special kernel from Google, and now the vendor can just add an extension to it. Now, PKVM is kind of the logical extension of that, where we're going to try to make an hypervisor that works for Android and that will be used across all Android devices, as to make things as standard and as simple as possible for Google or anybody else to change things up in there. So this is huge because the more we standardize this, the more we're able to make things that aren't locked by a vendor. If we all use that standard generic kernel image, we can change that generic kernel image for another, just keeping the special vendor module, and now we have a working phone with a new updated kernel that we have the control over. Same thing with PKVM, now we have control over the hypervisor, thus we can do much more than we were able to do before, while still being somewhat compatible with the overall Android architecture. So now let's drop to the file system, where we can talk a little bit, as usual, about Bcachefs. Now, there was a couple of things that happened with Bcachefs this release. There was Kent Overstreet that says that he thinks that his FS will be able to be stable by next year. He also claims that some part of the FS are 3 to 4 times faster than XFS because of the way that it multi-threads some operation. There also was some report that there was 40% less bug than before inside of that release, so that's good news. Now, the big problem, as usual, comes from the dev overall work ethic isn't really the right word, but his ability to cooperate with others. So, as usual, we have the good old Linus. Let's start by Kent that violates some kind of kernel rule. Linus that comes back and says, "Hey buddy, you shouldn't do that, that's a bad idea." And then Kent goes on saying, "Hey, it's not my problem, I don't care, and BTRFS is garbage, so I want to trash BTRFS some more." Then Linus tells him that he's a dummy. So again, we had that whole debacle. I'm not really going to talk much about it in this video because, well, the last two kernel video, we had a little bcachefs segment. I feel that as of now, if he still messes up like that, Linus should have the green light to remove him from the kernel. I mean, there's some point where enough is enough, and I think that we've passed that a little bit long ago. So let's go on to XFS, which, as we said, there's the bigger page size, bigger block size than page size that has been implemented here, which is nice, but also we have a new IOCTL, which is a system call to swap content between two files. So you can take two files and just exchange the content of both, which is cool. Again, XFS having all of the advantages ahead of the other FS, which is nice. And now we have Fuse that gets ID mapped mount support, with the first FS getting it inside of Fuse being VirtIOFS. Now that's nice. ID map mount, of course, is there to expose different mount and different file and directory to different ownership, meaning that you could have a home directory that could be transported across multiple computers. Now that makes a lot of sense inside of a file system that is meant to be accessed by a virtual machine, because we don't know the actual permission that are onto that virtual machine and onto the host, so it's good that we can tweak those through ID mapped mounts. Now we also have some great improvement from NFS, so the network file system, which adds the Localio protocol extension, which detects if the host and client are on the same machine, and if that's the case, it will bypass the use of XDR and RPC, which, if you want to think about it, is a little bit like packing whatever data you're trying to send in a box. So what we're doing right now is we're taking that data out of the box. We're not even putting it in the box in the first place. We're just throwing it because we're on the same host client or on the same machine. So we don't need all of that packaging. So now we're throwing data in a more direct way through the Localio protocol, and that yields us up to 10x improvement on reads, which is insane. We also have a file system that I didn't think we would ever talk about, which is 9p, which was made for Plan 9, which is kind of a weird file system because it's half an API and half an actual file system, but there was some code that was added that allows an host computer through a USB to share the file system, which means that, let's say that you have some kind of Internet of Things device or any small thingy that you want to have some kind of OS onto. Well, what you can do is you can connect it through USB, and if you have the right program to be able to open that share from the USB, well, now you can just host the image that you want to use as an OS onto that little thingy. So it can really help programmer to be able to, in a fast manner, be able to modify through USB those small gadgets. And now we have HeroFS, which is a read-only file system. Now what it gains today is the support for file-backed mount. So what it means and what it will be used for is to be able to mount the image from the file system without having to make any other loopback block device or any other things in memory that you wouldn't want to manage. So it makes everything simpler because now you can just throw your image that you would mount often into that file system and have kind of a trusted place for those images that can be mounted directly from there. So it makes everything easier to manage for sysadmin that would have, let's say, a big array of containers or VMs that they would want to run with image inside of a trusted file system. We also see from F2FS and BTRFS some small optimization, including some folio conversions, which, if we remember, in Linux, all memory is managed in pages, and folios are just a weird kind of memory where you have a bunch of pages together, and that makes things a little bit faster when we're talking about big chunks of memory. So instead of trying to manage thousands of pages, you put them all in a folio, makes things way faster to manage. So implementing that through F2FS and BTRFS makes things way better. Now our last change in the file system world is IO urang, which adds async discard support. Now that helps us a lot because application can now issue async discard rather than blocking the whole IOCTL discard because they're waiting on a synced discard. Meaning that most of the time when you want to discard something, when you want to delete something, you're not really looking at, oh, can it happen like now or it needs to happen in that specific order? You really don't care about that. You just want it to be deleted as soon as possible. So that's what the async discard does. It just doesn't bother syncing things and making things in order. It will just go ahead and do what you want it to do. So it yields us performance boosts. Now let's jump onto Intel in the architecture world, which now is out of the Family 6 era of systems. So in the kernel, you have a model ID for CPUs, and you also have a family ID. So since 1995, with the Pentium Pro, well, all Intel CPUs use the Family 6 name in order to identify themselves for their family ID. So now they're switching it up to the new ID that they're going to choose, which is fun. It doesn't change anything, but it's funny to think that in the mind of our computer, the Pentium Pro was the exact same family of CPU than your brand new Xeon. And talking about brand new Xeon, we have new model IDs that have been added for Panther Lake, which is the 2025 future release of CPU, and Diamond Rapids, which again, late 2025. And if you want a fun fact, Diamond Rapids, that's actually the big Xeon with 9,324 pins behind them. Yes, this is a monster. So I'm excited to see those, but we are seeing more push from Intel for those specific CPU, including a very small initial push for the drivers on the Panther Lake side. And I feel that I'm talking more and more in the CPU world about latency, efficiency, and how they go about optimizing a CPU with the exact same CPU, just working around in the software to make it better, faster, and use less current. And that's really great, but we have the new efficiency latency control that was added to the CPU. And what it does, well, it's exactly that. It uses two thresholds, one upper threshold and one lower threshold. And what it does is when you're going up in request for the CPU, let's say your CPU is running at 100%, well, your CPU will clock slowly up in 100 megahertz increment, and when it gets to a little bit lower, let's say at 50%, well, it stops so that you still have the best bang for your buck performance per dollar of energy inside of the CPU. Now, that's really good because it allows your CPU to technically run extremely low if it's doing nothing. And in big server farm, that's exactly what most CPU are doing most of the time. So you would want them to run at their minimal 800 megahertz to be able to save as much power as possible. And that's what they're able to do now. So if they need to pump up to 5 gigahertz, well, they're able to. And if they need to run at 800 megahertz, they're able to as well. So of course, that being a new feature, that's only a Xeon thing for now, so don't expect this to work with your i7 that you have at home. That's something that we're going to see more and more in the future, but for now, it's only a server thing. And talking about being jealous about Xeon CPU added the structural-based functional test at field, which is part of IFS, which is the testing infrastructure of Linux. So the goal here is to be able to test the CPU while it's running and that it could be as fast as possible. So they added a bunch of small tests that they can do, and what they do is they tell their new Xeon 6 Granite Rapid made by the end of 2024 that, hey, I'm going to use that core, let's say just one core out of the how much they have, but they can target one core and tell that core, hey, isolate yourself, and now I want you to do that test. And that test take 100 to 200 milliseconds, so it's a really fast test, and they can do it core per core. Now, that's really useful because you can do this in a server farm to make sure that, well, you don't have a CPU that's dying. You actually have a test now that is able to check to make sure that each part of the CPU work and is testable, and you don't have a special defect that would, well, make you lose some client's data. Now let's come back to a place that we can, us normal people without Xeon CPU, enjoy a little bit more, which is enhanced support for ENP core without hyperthreading. Now the scheduler is able to handle and understand those asymmetrical CPU, because before, for some reason, if you didn't have hyperthreading enabled, your scheduler would kind of not really understand that you had a special Intel CPU with weaker core that are more power efficient and power core which are there to, of course, push as much as possible and get the shit done. So now it being able to still understand that you have that asymmetrical CPU without hyperthreading, well, that just makes sense, right? It's not because you don't want to split your cores into to have hyperthreading that it means that you don't want to have a scheduler that actually works for your CPU. Now let's switch on to AMD, which has a lot of change of their own. We have the AMD P-State driver that has been reworked for its calculation for the AMD Boost and the AMD Preferred core detection, which should yield some small performance boost. We also have the runtime average power limiting code that was added for the new 1AH Zen 5 CPU, which allows to do the power monitoring work that lets us know what's going on with your CPU. We also have AMD that finally supports bus lock detection. Now, Intel back in the 5.13 release, which is 2021, added bus lock detection to their CPU onto the kernel, and now AMD is doing the same. Now, bus lock is something that happens when you have a CPU core that is trying to do an operation through to cache line. So inside of your CPU, you have multiple cache line that store cache data to try to make each core faster. And if you're trying to do something between multiple cache line, well, what you're doing is telling another core or all of your cores to wait a minute and actually let me get that data that you have on your side, which is thousands of times slower than a simple atomic operation. So it really disrupts performance. So this is the valid reason why we would want to detect that and be able to make sure that it doesn't happen, is because you could have a specific process that would abuse that and do it often, which would, well, bring your system to its knees. And now let's switch on to Long Arch, which has ACPI BGRT support, which is the little implementation inside ACPI which allows for splash screen integration, so having a little logo when you boot your computer. So that's good for them, I guess. We also have a KVM speedup for ARM and x86 binary translation. So the way that they're accelerating this is because there are 4 registers inside of the CPU that allows for some special flags that are used often. So it speeds things up to be able to use those registers to, well, emulate, or in that case would be translate, ARM or x86 binary. We also have the support for the generic CPU vulnerability reporting that's inside of the kernel. Now, that generic CPU vulnerability reporting is there to be able to report, hey, let's say that I have the meltdown vulnerability. You can check if a given CPU is affected, if it's mitigated, if it's not affected at all. So from the user space, you're able to kind of request, hey, is this a problem on that system, or is this a problem on that system? So now Long Arch has support for that. Now there's also RISC-V, which adds support for the same thing. So we have generic CPU vulnerability reporting on RISC-V as well. And let's talk about them a little bit more, because they're doing things that I like using their ZKR, which is a special entropy source extension inside of the CPU. So remember, entropy in our case means random, it means cryptography. So inside of the CPU, we have that ZKR part of the CPU that can give us randomness. And what do they use it for? They use it for kernel address space layout randomization, which is a part of the kernel that is there to ensure that your address space that you will use for your kernel is at somewhere random inside of your memory, because you wouldn't want your kernel to always be at the start of your memory or at somewhere specific, because if you do that, well, it's really easy to try to abuse some kind of vulnerability that you would have in the kernel by filling the data with some things that would, well, mess with the kernel once it's there. So it's great that we can use this randomization, this source of entropy, to be able to have even better randomization. They also added a new instruction, which is SVVPTC, which is an instruction meant to obviate memory management instruction after marking PTE as valid. Now, in plain English, that means that in some circumstances, you don't really need to do a bunch of work after adding a page table entry, a PTE. We don't always have to do some management of the memory afterwards. Normally, you would have to do some task in the background, but sometime when you're on the same hardware thread, you don't really need to do all that management of that memory afterwards. So it's kind of a command that's there to skip a step if you don't really need to do that step. So it's really a specialized command that both you and I probably will never use, but it's good that it's there, because some person smarter than me will be able to take use of it. So just a way to speed up the management of the memory inside of the CPU and the kernel. Now let's switch on to graphic and audio, where Intel enabled their Lunar Lake Z2 graphic and the Battle Mage graphic by default, following the initial support that we saw at the last kernel. We also see that the hardware monitor can now display fan speed for Intel discrete graphic card, which is kind of funny to think that there was no way to see the fan speed of your graphic card before. So nice thing, guys. Now we also have the Panther Lake CPU, which is 2025, remember, that now supports HDMI audio, always good. And we have some cleanup. They cleared out legacy audio Intel driver, which were deprecated by the newer Intel AVS audio driver. So they're replacing a bunch of drivers meant for Broxton, KB Lake, Skylake, Cannon Lake era driver, and they're replacing it by the newest Intel AVS audio driver. Now, it's kind of a span of 2015 to 2018. All those drivers switched to the new one. That's great. Now, on the AMD side, we see continued work on the RDNA 4 GFX12 hardware that is coming in 2025. Now, remember, back in the last release of 6.11, it was good enough to be enabled by default, but always remember that in the graphic and audio world, well, enabled by default doesn't mean much. It really only means that it kind of works, but we probably need to do more. So that's a good thing that we have support for it. We also have overdrive overclocking support for SMU14 hardware, which I couldn't find which hardware at the system management unit with the version 14. So yeah, you're gonna have to guess for that one, but it's good that we now have the ability to do some overclock for that hardware. And while we're at it, DRM, which is the part of the Linux kernel that is there to try to handle everything graphic, has the optional setting to display a QR code during kernel panic events. So it's way easier for us to scan our screen than actually reading whatever the hell was posted to the screen and is, in all likelihood, cut down by the screen size. So now we have a QR code for that, which is awesome. And by the way, it's in Rust. So let's go next to the network of the kernel, where NVIDIA is making some big change to their approach to the kernel. They added the MLX5 driver, which adds multipath PCI support, which is pretty much there to be able to do remote direct memory access, so have another computer look inside of your memory without you doing anything. So it allows big cluster of computer to share tasks that they need to do. Now, that in and of itself isn't really that interesting, but we have an NVIDIA engineer that made the statement, Jason Guntrow. I'm sorry I butchered your name, and the guy's Canadian. How could I do this to him? Anyway, he says, the new multipath PCI feature is a sign of things to come. I think we will see more of this in the next 10 years. So it's good to see that NVIDIA's engineer are getting, well, a little bit, they're getting on the hype. They like to see the amount of works that they can put on things that matters to them. So it's good to see that NVIDIA is taking the kernel more and more seriously. Now, another thing that I really liked in that release was the support for device memory TCP. So the ability to do a zero copy, receive a TCP payload, and dump it into a DMA buff region of the memory. What does that mean in plain English? In plain English, we can now receive a TCP packet and drop it directly to a PCIe device, meaning you can drop it to the memory of your GPU, you can drop it to the memory of your AI accelerator, you can copy wherever you want, but when I say copy, it's not really copy because it directly gets there. You don't have to do a copy. You're not limited by any other part of your system. You're not filling any bus up because you're doing some kind of copy of that TCP request that you received. And what's fun is that it's not something that's kind of dumb and that you would lose the packet header in the way. No, the packet header still lands in the right place inside of the kernel buffer. So you both have the normal kernel buffer, which is able to handle that TCP request and understand whatever you received, and the actual data inside of it that gets to the right place without any copying. Big for AI. So anybody that likes AI, that's a big one for you. And we were talking about Rust a little bit earlier, so we have a new Rust driver for the Applied Micro Qt 2025 PHY. Now that's a network card, that's not really much to think about, but it's a little bit showing that Rust is making progress all across the kernel. We saw it in the graphic through DRM with the QR code, and now we're seeing it in the network, and the last release we saw it a little bit everywhere. So we're really seeing Rust make way in the kernel. Now if you like Rust, you're probably happy. If you don't, well, that sucks for you. But in all honesty, we should really try to push for Rust to work, because love it or hate it, Rust is a part of the kernel now, and we should always do what's good for the kernel. So let's put our differences aside, let's try to make this work, and let's see if it actually does work. Now, let's get to the hardware, where we see initial support for the Raspberry Pi 5 SoC, so the Broadcom BCM2712, which needs more work, but it's good enough so that you can use your Pi 5 with a standard not patch kernel. So it's good news. We also have the new native PCI enclosure management, NBEM, which adds the specification from PCI Express that helps us manage LED lights that could be used for RAID drives enclosure. So if you have some kind of NAS enclosure, normally they're going to use as little part as possible. And using native PCI enclosure management, you're able to manage those LEDs that show you whatever, if you can remove your hard drive, or if you shouldn't remove your hard drive, or if your array is gone and goodbye your data. Well, now you can manage those LEDs through the PCI Express port, which is again good news. The hardware monitor now supports the SoftGo SG2042. Quick reminder, that's a 64-core RISC-V CPU that is clocking in at 2 GHz and has 120 watts of TDP. So yeah, that's an actual computer that's usable with RISC-V. And when I say usable, I mean fully usable. You can, with that amount of power, you can probably do some good dev work with that. So that's good news that we have hardware monitor working with that. Remember, the hardware monitor is everything that looks at power, that looks at fans, that looks at anything that goes with power management. Hardware monitor is there for that. And now we have a story about a guy that I really want to highlight in this kernel, which is Takeshi Sakamoto. Takeshi is the maintainer for FireWire, which is the only cable in life that I'm never thinking about. But somehow, this guy has made it his only job in life to support and maintain FireWire inside of the Linux kernel. So he says that he will support it through 2029. What an absolute unit. Come on, guys. The guy is supporting a dead cable at that point. Who uses FireWire for anything? Anyway, if you use FireWire, I'm sorry, I'm roasting you, but what an absolute unit. The guy is carrying FireWire alone, and that's good enough. We can give him a good clap. Now let's switch to a big change that has been made on the AMD side with the error detection and correction code, which now has the ability on AMD platform to translate normalized error address into system physical address using the UEFI platform runtime mechanism. We are going to need to roll back a little bit to try to understand everything that I said. So let's start with the error detection and correction. That's a part of the kernel that is there to try to understand what's happening with the PCI, PCIe, and the ECC memory. So if you have an error with them, well, this part of the code is going to try to fix it and try to make sure that we don't end up with a kernel panic, or if we end up with a kernel panic, well, that we end up with a kernel panic for a good reason. So in case that code receives an error from your ECC memory, so from the memory with error correction in them, the first thing that will happen is that it will do a system management interrupt. Now, what the system management interrupt does is it goes into system management mode. Now, for those that don't know system management mode, it's also called black box or ring -2 because it truly is a dark black box. You don't know what is running there. The system management mode is there to unscrew your computer when it's really screwed. So it's a place where your OS has no idea what's running, and it actually freezes your computer when it's executed. So let's say that I receive an error from my ECC memory, my system tries to have a clue what's going on, calls through the SMI, it calls the system management mode, and now all the cores on my computer are completely stopped the time that the system tried to manage and to understand what's happening and to vomit back to you an address. Now that's a garbage way to operate. We can all agree that stopping all cores of your CPU in order to unscrew whatever you did is not a good thing. So this is why PRM, platform runtime mechanism, was added. So this UEFI platform runtime mechanism is there to be able to give the OS some resources that enables the OS to do the same job that you would do with a system management interrupt. So you don't have to interrupt your whole machine in order to be able to locate where the physical address is. You can just use the resources that PRM is giving you. So this is why it is really good that the error detection and correction code now has this ability to use PRM, is because now we can actually bypass the system management interrupt, which would freeze our whole computer for a simple error from the ECC memory. So good on you, AMD. That's a really good one. I like it. Just like I like this new feature that was added, which is the ACPI CPP-C code that now allows the setting of the EPP, the Energy Performance Preference Register, through the functional fixed hardware address space. In English, please. So now we can pass through a CPI in order to change the energy performance preference, which is a little place in your CPU that is there to say to your CPU, hey, do I want to push on the gas pedal a little bit faster, or do I want to hold back a little bit more? So those registers are there to kind of direct how aggressive your CPU should be about power. So those registers are really important, but on some machine, like some Asus AMD system, you cannot directly change the EPP through the standard channel, through the standard command with your CPU. So being able to pass through a CPI, in other words, passing through the firmware, you could say, it gives us a new path to actually modify those EPP values, which again are really important for performance. So if you want to modify them in order to have a computer that would be better at, I don't know, managing the games that you're running or managing the workload that you're running, well, now you can, even on those machines that wouldn't traditionally allow you to. Good work, again, from the kernel devs. Now let's go to virtualization, where VirtIO VSOC now avoids queuing packets when the immediate queue is empty. Now, remember, VirtIO is kind of the tool that you use inside of KVM in order to do a pass-through from your host through the guest. It can also be used in the case of a VSOC, which is a kind of a socket that tries to avoid all of the big baggage that comes with a network socket. So normally, if you would want to pass data from the host to the guest, well, if you use a network socket, it's going to be polluted by IP table, by net filter. We don't want that, right? So what we're going to do is we're going to have a socket that is as simple as possible, which is the VirtIO VSOC. Now, avoiding queuing packets into a queue if it's empty is just a good way to optimize the process, and it also yields great result. We can see it on screen right now, but it allows us to have more performance without doing anything. Just don't queue something that doesn't need to be queued. Now, KVM will also advertise AVX 10.1 to the guest VM, which is a package of Intel instruction that will now show when the guest requests the CPU ID. So normally when the guest VM would ask for it, well, the host would never answer with the real answer. It would just say, no, I don't do those instructions. And now that KVM can work with those instructions and can now display to the VM, to the guest, that it actually uses those. So there can be some optimization there. And let's just move to Hyper-V that has a big code boost, which allows multi-core CPUs, so big machine with like 1,000 cores, to be able to be initialized in parallel. So before, they would do it sequentially, meaning that you would do one CPU at a time in a really, really, really slow fashion. And now when you're opening up the Hyper-V code, you don't have to initialize them sequentially, you can do it in parallel, making it, they say 66% faster, but let's be honest, if it's only 66% faster, that's kind of crazy how the sequential one was fast before. Anyway, let's go on to security, where we have good news. Remember, in the last release, we had the VDSO, which added get random support. Remember, the VDSO is kind of a part of the Linux kernel that is displayed to any program, and the goal of that part is to be a kind of library. So if you want to run a special line of code, you can use the Linux version of that code that makes things a little bit faster. Now, the support was there for some infrastructure. Now it's been added to ARM64, to PowerPC 64-bit, PowerPC 32-bit, to X390X, long arch 64-bit. The only missing one is RISC-V. So we're working on that. We're working on RISC-V, going along with all of the other cool kids here. But yes, the VDSO get random command is supported by most. And we also have Golang, which enable it. So remember, you need the library or the compiler to be able to understand that the VDSO has this feature in order to use it. So now Golang has this enabled. It can use that feature. And for those who like to live dangerously, you now have the option to compile your kernel without specific mitigation inside of them. So you don't have to use the good old command mitigation off at boot time in order to get the same result. You can just precisely kill your computer with the kconfig option for the given vulnerabilities. So good on us. We don't have to worry about anything. Let's just run without any mitigation and ensure that we get hacked. We also have the new integrity policy enforcement mechanism. That is a mechanism that relies on the immutable properties of a given storage in order to restrict or not its ability to execute. Now, in a more clearer way, you only can execute what is immutable, what cannot be modified, and it kind of removes the possibility for foreign code to break your system. So there are some part of the Linux kernel which are immutable. When you run your system, you can also choose some kind of file system that would be in read-only, that would be able to ensure security of the code that you're running from there. So using the IPE, the integrity policy enforcement, you would be able to run only those specific part of the code so that you don't ever have a problem with foreign code breaking your system. But there's something that I truly know that is good, is that the Linux Security Module Subsystem, LSM, now uses static calls instead of indirect calls and return trampoline. Now, for those that don't know, indirect calls can be affected by the Spectre vulnerability. Since this vulnerability has been corrected through mitigation, it means that all indirect calls are a little bit slower because they use branch, they are conditional, meaning that Spectre vulnerability can apply, thus slowed down by the patch. So the solution for that was using return trampolines, which are kind of a secured way to do an indirect call, but they are far slower than an indirect call. So they came up with a solution which is a static call. I'm going to be totally honest, that's a little bit like dark magic to me. I'm not sure I totally understand how it works, but what I know is that it gives more security and more performance than both the indirect call and the return trampoline, which is great. So they're seeking to transform more and more part of the kernel that uses those indirect call and return trampoline. And of course, the Linux security module would be a really important place to have maximum amount of security. So they have switched all of those into static calls. Now let's switch to our extras, where Linus added user access fast validation via address marking. So there has always been a command that has been there to be able to check if a pointer points to memory that is safe to use, meaning that it's not part of the kernel, that it's not something that you wouldn't want to access. And that command would be access OK. But since Spectre, well, it's slowed down because it's used conditional branches. So what they did is they did a new way where they're using address masking instead of a conditional branch, meaning that you can confirm that the memory you're trying to access is safe to access without breaking the whole speculation barrier problem with Spectre. So a faster way, while not using the old way, which is a little bit slower, But from what I see, you need a little bit of a setup for it to work. It's not something that you can just put in place at the exact same place of the XSOK command, so I don't know how much it will be used, but hey, it might be useful for some. Now we also see the EEVDF scheduler, which has been completed, and it should phase out CFS, which is the standard scheduler for Linux, in the near future. Now it's great because this new scheduler should improve latencies and responsiveness in a lot of situations. Now let's talk about sched deadline, which has a big change in the kernel. Now first we need to understand a little bit how sched deadline works. So it's a scheduler, of course, but the goal of sched deadline was to be able to, well, as all scheduler, be a little bit fair. So the way that it works is that you have a task that wakes up. This task should have a relative deadline. So that's a deadline that it declares to the scheduler in order to run correctly. That compute time should fit inside of that deadline, and if it doesn't, at the end of the deadline, you would run another task until you come back at the end of the period where you would be able to run again your small piece of code. Now that's a fine system and all, but at the end of the day, you don't really have all tasks that are fitted with the deadline parameters, which are a runtime, a deadline, a period. In other words, you have some standard task that just uses a standard first in, first out kind of way of working. So some task will just throw themselves out and just say, hey, run me. And there's other that will have the whole sched deadline scheduling infrastructure at the back of them that will tell the scheduler exactly what they want. So the issue comes that, well, if you have some deadline process, the whole deadline parameters attached to it, well, it would be able to kind of take all of the CPU and starve all of the other tasks from working. So all of your other FIFO, all of your other first in, first out process wouldn't be able to run, or not as much, because your CPU would have been starved because of those other tasks that declared themselves correctly. So the way that they kind of solve this problem is to have a deadline server, and when they would detect that deadline task would starve the CPU, it would wake up and make sure that some FIFO task would run to allow some kind of fairness, because we can kind of understand that not all our tasks are going to be marked correctly, and for the small task that isn't marked correctly, being delayed indefinitely isn't a fun thing. So it's really good that we have that change inside of the kernel to actually make the most out of sched deadline as a scheduler. We also have sched util, which is the CPU frequency scaling governor, which is dropping the good old latency multiplier. Now the way that sched util would work is that it would be called once every 1,000 times that it takes for the frequency on your CPU to change. So let's say that it would take 2 nanoseconds to change your CPU from one frequency to another. You make that times 1,000. That would be how often your sched util would be called. Now they kind of had a problem with that because that transition latency was a little bit too big for modern CPU, meaning that it would be absurdly long for sched utils to be called. So they decided that, hey, we're going to put a ceiling on sched util. If it takes more than 2 milliseconds for it to run, just run it again. So they put that ceiling, but now we have a problem where every computer that's working with Linux right now will be hitting that 2 millisecond ceiling. So you will always be running at 2 millisecond intervals. Now that still doesn't really work, right? We want our sched util to kind of work with the CPU and be as responsive as possible. So the way they fix that is, well, it turns out that if you multiply your transition latency, which again is the time that it takes for you to transition from one frequency to another, if you multiply that by 1.5, it will make it responsive without drowning your CPU in request. So they made that change to schedutil so that we can now play with frequency with a little bit more precision. Now we've also have some work on the XZ embedded code, which is the code that is there to mostly decompress the kernel, which has changed license to the BSD zero clause license, which is pretty much I'm not liable for nothing, end of it. So it also adds support for ARM64 and RISC-V, which are two platforms that were waiting eagerly for that support, so that's good news. We also have the extension of what we saw in the last 6.11 release, where we had the make pacman package command, which was able to, well, make a pacman package of the kernel. Now we can make a debug package of the kernel through pacman again. So that's good for people that work with the kernel, debug the kernel on Arch Linux. They're actually able to get it done through pacman. So we have a build of the kernel with the non-strip VM Linux file, all the debug symbols that are necessary for debugging and the performance profiling tool, everything in there, all that we need to work on that kernel. So good for those people. We also see full force being removed from the kernel. Now, we're going to need a little bit of background to be able to understand that. Now, inside of the Linux kernel, you can go see inside of /proc/ and if you get the process ID, you can do /mem to be able to see the actual virtual address space, the actual memory of a given process ID. Now that's all good and all, but sometimes you would want those address of memory to be, well, protected, right? You wouldn't want all the memory to be readable. So that's what the kernel does, naturally. And there's a command that was made to kind of go through that and just read the memory anyway, which is mem rw with the full force command. So that's kind of a problem, right? Having a command that can just snoop through memory and not give a shit, that's not something that we want, right? And being able to override that memory, again, not something that we want. So that was kind of known as an exploit and as something that nobody wants to happen. But the big problem is there is actual code that uses this. So you cannot remove it because you're removing actual working code for some people, but you need to remove it because, well, it's a big hole that you want to patch, right? The solution that they kind of came up with is that you have three options. You have option 1, which is I'm dangerous, everything is open, you can use full force for any reason. You have solution 2, which is, well, you can use full force, but only for ptrace, which is pretty much the main tool the debuggers are going to use full force for. So it makes sense that you would make an option only for ptrace. And there is the final change, which would be full force being completely disabled, which would be most people. So it's good now that we have some kind of granularity. We have a way to actually correct this and let the option for the people that would want that option to still work. Now, it's way better than other options that were given out there, because before there was the proposition to actually make this level of granularity for each process. So each process would have the ability to restrict full force being applied on it, which would be a little bit insane as a setup just for one command. So I welcome that change. That's good news. That's a good patch. That's something that we should be proud of. Now let's go into a declaration by Sasha Levin, which announced that there would be a new tree that would be created to perform some integration test. And that tree would be called Linus Next. So just so people understand, in the kernel, you have a place called Linux Next. Linux Next is there to be able to shove something into the kernel and to test if they actually work with all of the other things in the kernel. So what you do is, hey, I have a new feature that I want to add to the kernel. I'm showing it into Linux Next, and if it works, then you can go to Linus and you can tell him, hey buddy, it works into Linux Next, merge it, and it probably will end up being merged. Now, the idea behind Linus Next is the same thing, but with a little bit more control from Linus, meaning that it won't be a garbage pile like Linux Next, because the big problem that people have with Linux Next is that there is so much things in there that you end up with some code not working, and it doesn't work not because you have made a mistake, but because some other dev somewhere has made a change that for some cosmic reason causes a problem with your code. So it kind of fixes a problem, and at the same time it creates one, because if really we have a branch that is a new tree that is named Linus Next, well, that's confusing. Linux Next. Good luck with that. So I'm going to let the LTS kernel maintainer deal with that and defer to their authority. If they think it's a good idea, I'm gonna say it's a good idea. Now I can tell you something that is not a good idea, and that's Linus being frustrated by bad CPU design. We have a good quote from our good dictator, Linus, which says, "Honestly, I'm pretty damn fed up with buggy hardware and completely theoretical attack that have never actually shown themselves to be used in practice. So I think this time we push back on the hardware people and tell them that it's their damn problem." So you can kind of feel that Linus is kind of getting fed up, and that was because of a new instruction inside of an Intel CPU that was kind of not really possible to fit inside of the existing kernel, and it was, like he said, to fix a completely theoretical attack, not something that has been shown in practice. So kind of weird. It's not something that Linus should have to shove his head into a wall about. It's not something that he should have to work on. Honestly, CPU designers should really speak a lot with the actual kernel devs in order to know what they need so that their CPU can be useful. Now, this is actually a little bit funny because Linus is now part of the x86 advisory group, so he can actually now yell to the CPU makers directly, which is, yeah, that's a good one. I wanna hear that Zoom call with Linus just just losing his shit. Okay. And another group of people that lost their shit, and that's actually a little bit sad, is that some maintainer were removed from the Linux kernel. Turns out that those maintainer were all Russian, and well, you can kind of understand the rest if you have two neurons, but there's kind of a big problem of legality when you have a big organization like the Linux kernel, is that you don't really want to have people that have sanction against them working onto your kernel. So because of that, like I said, some Russian maintainer were removed. It was done rather swiftly and not in the most respectful way, we can all agree. So one of the Russian maintainer was a little bit frustrated by that and saddened by it. It's sad to see that, well, what's happening globally hits people in different ways, and in some ways hit people that really shouldn't be hit at all. But sadly, when it comes to legality, we cannot really just say no to sanction, right? We need to remember that the law is over whatever the hell we're doing inside of the kernel. You cannot just say because you disagree with whatever war is going on or the support for a given war, it's not because you have a given opinion of that you can just bypass the law. So it's sad, but we should still breathe in, breathe out. We're gonna go through it. It's sad for those people, and we can share their grief. And now, just because I needed the clickbait title, we have a crazy optimization of 3,888.9% for a one-liner due to some mmap code that didn't check the alignment inside of the transparent huge page code. Now, this is this is just the funniest test ever, because they're kind of testing one function that gets called once in a lifetime. It's not something that will change your life, right? It won't change anything to you using the kernel, but for some reason they decided to change the code and actually test how much their optimization changed the result, and it ended up being 3,888.9% performance gain for some random memory map code. So good one, guys, good one. That was worth it. One-liner. That's a good optimization per line right there. We've got it. We have a last-minute commit that went in right before the release of this kernel. So they patched a bug that was happening with Ryzen 7000 and 8000 machine, which when you would have nested virtual machine on the machine, there was a command that could be run that would actually freeze your old computer. Well, more than freeze, it would shut it down without any log, without anything. So your computer would just 100% die if you had some virtual machine do a specific command, which of course is really, really bad. You don't want that to happen. And of course, the only thing that they did is just remove the ability for the virtual machine to use this command, and remove the fact that the virtual machine was saying, hey, you can use this command, and that would of course do the problem. So it's good that they fixed it. We're all happy for this. This was a really last minute change. And well, if you're there right now, you're in the editor's note. So you're at the last minute. We're doing those notes after all of the editing is done. We're just adding things at the end. So I'm really happy about how this video turned out. I hope you really liked this video. And if you did, drop a like, subscribe, of course, if you're not already. It's really fun to have also all of your comments. I like that. And thank you a lot if my friend who did a donation last time. Really good. That's good for the morale. Having a little €5 really feels good when you're putting that amount of work into a video. If you want some spoiler about what will be upcoming, we are going to have an EXT3 video, because you know, if you follow me, there was the EXT2 video, which was really great, and we're going to have the same quality into an EXT3 video, which is going to be as awesome. There's a lot of research there. We're going to learn what H3s are. We're going to learn how journaling works. We're going to learn the change that were on the actual hardware. When we're writing the bits, we're going to see what was added. It's really awesome. So stay tuned for that. Subscribe, all the good stuff. And of course, take care.